Hello and welcome to the StarSailor podcast with Peter Clark and Hannah Hutchins. Now we're on to part 2 of our interview with Professor Bill Keel on AGN. We left off with Professor Keel about to go on and explain what radio galaxies are.
Then, as radio astronomy developed in the 1950s, and particularly as the technique of interferometry was refined, it turned out the sky is full of a particular pattern of radio sources, which is two lumps of material producing radio emission on either side of a galaxy that we see visible light. These came to be known as radio galaxies. And as we refined radio techniques, we find that very often these two blobs of radio emission are connected to the center of the galaxy by jets. So that was another piece to the puzzle, that whatever it is producing the energy in active galaxies traces back to the center. It has an axis. It can send material out in two opposite directions, and it can do it for a long time. If you see a jet going out a million light years, it's taken at least a million years in the same direction. Then just a little after that, quasars started to be identified. Originally, these were difficult family members of surveys from radio sources, things that couldn't obviously be identified with supernova remnants in our galaxy or bright galaxies nearby in the universe. There was nothing in the field of view except what looked like stars. So radio astronomers had to refine their positional techniques to figure out which one of those starlight things it was. The starlight gave rise to the notion that they were quasi-stellar objects, shortened quasars. The original quasars had strong radio emission, and when they do, they look a lot like radio galaxies. They have the two lobes and they have jets. They are spectroscopically like Type 1 Seyfert galaxies. In fact, you'd have to be really a specialist to distinguish just from the spectra which one was which, but they're enormously luminous. So the first things that we could see far across the universe, quasars, because they're so bright. So we see connections here that the radio structures of quasars can be like radio galaxies, though it turns out not all quasars are powerful radio sources. And they have commonality with Seyfert galaxies as well. And just as with Seyfert galaxies, evidence accumulated that in some cases what we see as a radio galaxy is a quasar seen sideways. So the core is blocked by gas and dust from our direct view. And sometimes polarization, for example, shows us the dim reflected light of a hidden quasar. Adding to the confusion was another category of active galaxies known as blazar. The first of these that we knew about was called BL Lacerti because it had originally been cataloged not as a galaxy at all, but as a variable star. That's a variable star name. But it showed variability, but not with any particular pattern. And photographs showed that it was a little bit fuzzy because the core is so bright. It took special techniques, I'm very pleased to say, carried out by a couple of students along with my thesis advisor before I got there, to isolate the spectrum of the fuzz and show that this thing lay in a galaxy at a redshift Z of 0.07. And other objects of this kind show up. They were very frustrating spectroscopically because typically a BL Lacerti object shows no spectral lines. The spectrum is completely smooth, defeating attempts to measure its redshift. So data on them accumulated rather slowly over years. They show rapid variability, high and variable polarization. They're often very strong radio sources. And all these could be put together with the idea that here we're seeing a quasar or radio galaxy where we happen to look right down the jet. The jet is nearly going the speed of light, and in this case, it's coming right toward us. And with some effects that Einstein showed us with special relativity, from our point of view, it appears much brighter and boosted to higher frequencies. So the jet is almost all we can see because it outshines everything else. So over and over, we have this theme that the structure of active galaxies has an axis, it has different locations where it looks quite different. So the idea that this viewing direction is very important has been fruitful. So we have the idea of how powerful is it, how fast is the black hole accreting matter, and what's the direction that we see them from. That doesn't explain everything, but those are clearly key concepts in understanding why observationally we see all these different kinds of active galaxies. But in fact, we may be seeing, in a lot of cases, one standard structure with a volume knob and angle change.
What effect does an AGN have on the star formation in its host galaxy?
That's something we'd really like to be able to pin down with data. There are hints that an active galaxy is at least associated with changes in a galaxy's star formation. This comes from looking at star forming regions in the inner part of galaxies It comes from looking at the statistics of galaxies. Certain properties of the brightest galaxies and which galaxies are making star formation at a particular time are best explained if at a certain point in the growth of the central black hole, it shuts down star formation, so-called feedback. This also fits with a property of galaxies that really only turned up, it really only became obvious with data from the Sloan Sky Survey. We'd appreciated for a long time that galaxies with no star formation are very systematic. They have very clear, reproducible behavior involving their color and luminosity, the so-called red sequence. What wasn't so clear was that there's a wider but well-defined blue sequence of star-forming galaxies, and there are so few in what's called the green galaxy in between that most galaxies can only make that transition once. When they run out of fuel for star formation, they transition to the red sequence and slowly fade across the green valley. The interesting and unexpected thing is that if you look at how many of those are AGN, for example, using spectrum from the Sloan survey, the fraction of galaxies with AGN is greatest in the green valley. So somehow this powerful episode of feeding the black hole is associated with this one-time, perhaps gradual shutdown of star formation in the galaxy. So those two events are somehow associated. It's not completely clear which way it goes, but you have to wonder if at a certain feeding rate for the black hole, if its surroundings light up hard enough, do you blow material out, can you shut down star formation? Or how does that work? We know of at least some cases where feedback goes in the other direction, where jets from an AGN can strike interstellar gas in the same galaxy or even in another galaxy and compress it to trigger star formation where it wouldn't have been going on before. We see that in the very nearby radio galaxy Centaurus A because we can see the stars one at a time. We see it in some radio galaxies. In a case known as Minkowski's object, there's some poor, innocent, irregular galaxy that was just sitting there and got hit by the jet from a radio galaxy and lit up with star formation. And one of the things that we learned from Hubble data on Hani's forebear is that there's a small region there where material flowing out from the AGN has triggered star formation that we see nowhere else in this vast 900,000 light-year cloud of gas.
We've heard that some black holes are spinning and others aren't. So does a black hole that spin have an impact on an AGN within the galaxy, or does it have wider implications for the galaxy itself?
You know, a lot of people who try to understand what goes on right around the black hole, which is, at this point this has to be done theoretically because we have so few observations that have any bearing on it, have concluded that the spin, or more particularly the angular momentum in the black hole, may affect its ability to launch jets or the properties of those jets. It's difficult to have a massive black hole sitting in the middle of a galaxy that doesn't pick up spin, because if you form an accretion disk, that accretion disk has material all orbiting in one direction. If it falls in, it takes the angular momentum. A very curious thing is that the direction of the jets coming out of an AGN doesn't necessarily have to be lined up with the axis of the galaxy. So it's as if the spin axis, if you will, of the black hole can be very different from that of the galaxy. Maybe you can have that when material gets dumped in from a merger, or very local effects. But you can change the spin of a black hole only by throwing in enough material that you've added as much mass as you started with. So that may be going on as well. We're really just beginning to see how these effects might work. Some of the most powerful work is being done not on AGN, but on the black holes left behind at the deaths of stars. We can see those more nearby, and the system is often much simpler. So there's a lot of work going on in X-ray astronomy, looking at exactly how these flicker, how they change as they may move in orbits with their companion stars.
That's it for this episode of the StarSailor podcast with Peter Clark and Hannah Hutchins, but you can hear more of our interview with Professor Bill Keel on our next instalment.